For the last several years, the Coastal Processes Group at Scripps Institution of Oceanography has been posting an annual report on the physical condition of California's state beaches in San Diego County. A primary goal of the report is to describe the current condition of the beaches within the broader context of California's interannual climate patterns, particularly the La Nina, El Nino, or ENSO climate cycle. By quantitatively linking our observed beach changes to climate variations, we can use the data as a basis for future beach change projections with climate change. When viewing the report on our website, we encourage you to scroll through the Story Map guide if you have not done so already. It outlines the beach metrics we use and will help you interpret the report figures. We also encourage you to visit the overview page for each year before diving into the details for any particular beach. The 9 beaches included in the report are shown on this map of the San Diego County coastline. They range from Borderfield State Beach in the south up to Carlsbad State Beach in the north. Torrey Pines State Beach in the middle of the county has been surveyed more frequently over the last 20 years than any other beach, and I will use the data from the north end of Torrey Pines to describe recent wave and beach behavior in the county. The report uses beach years rather than calendar years, starting October 1st instead of January 1st, which is better aligned with our typical winter-summer weather cycle. The presentation will cover the two most recent beach years, as shown in this time series plot of nearshore wave heights at North Torrey Pines Beach. 2021 was notable for a single isolated extreme wave event in January of 2021, in what was otherwise an unremarkable wave year. And 2022 was notable for a long winter lull followed by an extended period of unusually high spring waves in the spring of 2022. I'll be discussing the response of Torrey Pines Beach to these wave conditions later in the presentation. The key metric we use to define a beach's physical condition is its annual mean beach width, with each state beach having a single value for each year. The beach width is defined as the distance from a fixed back beach line, to the MSL shoreline contour as shown in this illustration from the report guide. The surveyed widths are averaged over the entire state beach and the entire year to define the single annual mean beach width value, which I will refer to as simply the annual width of the beach. The report's overview plot tracks the change in annual width with the beach year, going back as far as we can with suitable historical survey data. Years with major nourishment projects are highlighted in color, and El Nino years are highlighted in gray. Using Cardiff State Beach as an example, the annual widths are shown as asterisks. We typically see a negative setback in the annual width during the El Nino years at all the beaches, so trend lines are fit to the data in the intervening years. These are used to define whether or not a beach is trending towards recovery and at what rate. The plot shows that the annual width of Cardiff has grown considerably between the last 2 El Ninos. The impressive growth can be traced to a combination of factors, including the annual bypassing of sand at the San Leo Lagoon Inlet and the natural retention of nearshore sand in this area thanks to shallow, rocky reefs on its north and south boundaries, acting like submerged groins. This has all made Cardiff a fortuitous outdoor laboratory for creating a sediment budget model built around the observed El Nino sawtooth beach evolution behavior. In the next presentation, Shri Gopal will be discussing how we are using the survey data at Cardiff to explore different climate-driven beach evolution scenarios out to 2050. This is the report overview plot with all the beaches on it through 2020. It is a lot to take in quickly if you haven't looked at it before, so I will highlight some of the important features for our discussion. Beaches that were widening since the 2016 El Nino setback, based on their linear trend lines, are plotted in the lower panel and highlighted in green on the map on the left. Beaches that were getting narrower are plotted in the upper panel and highlighted in red on the map. Looking at the map on the left, all the narrowing beaches are north of Cardiff. While we don't know exactly why this is true, unlike the state beaches to the south, many of these beaches have cobbles exposed year-round, not just in the winter, and cobbles don't behave like sand. Hiro will tell you all about this in his presentation. So this is what we were seeing up through October of 2020, with the beaches marching to the beat of the El Nino climate cycle in either a resilient or a non-resilient manner. But then 2021 happened. A singular extreme wave event, notable for both its size and duration, pounded the county coastline on January 25, 26, 2021. This photograph shows the surf zone extending out well beyond the end of Scripps Pier, which is an about 7-meter water depth, so the offshore depths to which sand migrated was significant. However, the rest of the 2021 winter was unexceptional, so the thought was that the beaches might bounce back quickly. But somewhat to our surprise, when the annual widths for 2021 were tallied after the following summer, the annual width setbacks were similar to the 2016 El Nino. This is our latest version of the overview plot up to October of this year. The extreme event in 2021 resulted in an annual beach width loss of up to 10 meters at some beaches, similar to what was observed in the 2016 El Nino, and they did not fully recover the lost width in 2022. As a result, we are giving 2021 its own designation as a setback year on the right-hand side of the plot with the red vertical stripe. And we are restarting the beach width trend line calculations like we do after El Nino years. Several beaches have changed their erosion accretion status with the 2021 extreme event reset and have been moved between the lower and the upper panels. Silver Strand is one of the wider beaches and previously had accreting trends between El Ninos, but eroded significantly in 2021 and continued to recede in 2022. It is now in the upper panel. Cardiff is also one of the wider beaches that typically accreted, but it showed the same loss behavior as Silver Strand. On the other hand, South Carlsbad had an erosion trend before, and while it eroded further in 2021, it recovered slightly in 2022 and moved from the upper to the lower panel. This shakeup in eroding versus accreting beaches may be short-lived, as the 2-year trends are not a true trend fit, but simply connecting dots at this point. We'll better understand the multi-year impact of the extreme events in the next few years with additional data points for the trend fit lines. The impact of a single extreme wave event is somewhat distressing from a prediction point of view, but assuming that future years are simply unpredictable is likely an overreaction. While 2021 was a surprise, it was not unprecedented. A similar event occurred in 1988, with the largest storm on record striking Southern California during what was otherwise a modest winter for waves. Like the 2021 event, it developed in a very un-El Nino-like way, relatively close to the North American coastline in a region where Pacific storms normally begin to decay. So we can conceptually lump 1988 and 2021 together as a singular extreme event climate phenomena separate from the El Nino cycle. When shown schematically over the last 50 years, the El Ninos and extreme events that result in major annual beach width loss have return periods of 3 different timescales. Moderate El Ninos, the blue lines, typically occur every 3 to 7 years, but result in lesser beach loss compared to strong El Ninos and extreme events. Every 10 to 20 years, there has been a strong El Nino in red instead of a moderate one. And now we have observed 2 extreme event years in green, approximately 30 years apart, occurring during non-El Nino wave years. For the remainder of the presentation, I'll talk in more detail about the beach response to the January 2021 extreme event compared to the 2016 El Nino. And I will also demonstrate how we can track the more detailed seasonal behavior of the nearshore waves and beaches by looking at 2022. North Torrey Pines Beach is our most comprehensively surveyed reach of coastline over space and time. Its annual width has been the most steady of all the beaches over the last 2 decades, making it a nice beach for calculating long-term statistics. I will use it as a proxy for general sandy beach behavior in the county. We have a research tool for studying the relationship between nearshore wave conditions and beach change, or the wave and beach climatology, that we call the Monitoring and Prediction, or MOPS system. With the MOPS system, we can link historical wave observations from the CDIP wave buoy network with historical CPG beach surveys along the California shoreline at what we call MOP lines. In this illustration for the shoreline at Torrey Pines, a selected number of the upwave CDIP wave buoys in the left panel are used with a propagation model to predict the hourly wave conditions at red points in 10-meter water depth in the right panel, all along the California coastline. On the subaerial beach and in the subaqueous steps along the MOP lines, we have our historical CPG survey data and a small number of surveys from other sources. I would like to take a moment to thank Ron Flick here, as the MOP system was one of Ron's earliest and longest investments as a program manager. Dick Seymour originally envisioned coordinated wave and beach data collection on regional scales, but it was Ron who got it done. The MOP system was used by FEMA for the waves portion of their most recent coastal flood map update for California, and the general framework was the starting point for the USGS Cosmos project in California. We will narrow our wave and beach analysis to a single MOP line, MOP 583, near the entrance to the south parking lot at Torrey Pines, as shown in the map on the left. On the right, I have plotted all the historical beach and wave data we have for this MOP line versus the time of year. The upper panel shows the mean high water beach widths, represented as a distance anomaly from their global average. The bottom panel shows all the past buoy-driven hourly nearshore wave height predictions. On the x-axis, we have the months of the year, arranged in our beach year format, starting in October and ending in September. By passing a 45-day running average filter through the data, which I'll call the seasonal average, we can create long-term average curves for both the beach width and the nearshore significant wave height at this specific MOP line. The long-term average beach width curve in the upper panel shows average yearly change of about 18 meters, going from plus 10 meters in October to minus 8 meters 6 months later at the end of March, and then recovering for the remaining 6 months of the beach year from April through September. The seasonal long-term average curve in the lower panel looks pretty flat in this depiction, as the extreme events can be nearly 6 times larger than the mean during the winter months. But I'll show you in a moment that departures from the long-term average using similarly filtered wave data from a specific beach year is highly correlated with similarly averaged beach width changes that year. So these long-term average curves are really useful for understanding both the past and future evolution of the beach. At this point, we can make reasonable long-term seasonal average wave curves for any state beach in California using historical buoy data and wind wave model hindcasts. The bigger challenge is making the long-term average beach width curve in the upper panel at state beaches that have not been frequently surveyed in the past. We currently have a graduate student and a postdoc working with historical satellite imagery, and we are cautiously optimistic that they can enhance existing image analysis methods to reproduce the seasonal curves at Torrey Pines, among other things. If successful, we could then apply those methods to other state beaches. So let's look at the 2021 beach year relative to the long-term averages. I have overlaid the 2021 seasonal 45-day running averages in red on the long-term averages in blue. What stands out in the upper panel is the large seasonal beach loss from January to May compared to the long-term average. Nevertheless, the beach did make it back to its long-term average width in the summer. This winter-long loss appears to be almost entirely the result of the extreme storm highlighted in the lower panel. I say this because the remainder of the winter season had slightly below average wave conditions, as indicated by the red line running just below the blue line from February through May in the bottom panel. So let's see how the beach loss for the 2021 extreme event year compares to the beach loss during the 2016 El Nino. In 2016, we see that the maximum seasonal beach width loss was similar to 2021, but the beach retreated sooner and never made it back to the long-term average in the summer. Looking at the waves in the bottom panel, We can see that 2016 had a double whammy of extreme events and well above average winter waves on the whole, which we did not see in 2021. Bringing the 2021 seasonal widths back for direct comparison as red dotted lines, this gives us some hope that the overall offshore displacement of sand in 2021 was not as severe as 2016, and our annual widths may recover more quickly in the next few years compared to after the 2016 El Nino. Moving on to the 2022 beach year, you can see in the upper panel that the 2022 seasonal widths in red stayed within the +10 and -8 long-term average range. However, they never really tracked with the long-term average and therefore exhibited very unseasonal behavior. This was driven by similar unseasonal behavior of the waves in the lower panel. In October, 2 unseasonally large early storms drove the beach width below normal. The dotted horizontal arrow in the upper panel shows that our average width at the end of October was where we would normally expect to be in late December. But then there were well below average winter waves from December through February. The average width changed little in response, and that led to the beach going from narrower than normal to wider than normal by the end of February. In March, waves were more like the long-term average in the lower panel, and the beach width narrowed back to its long-term average width in the upper panel in response. But then, above average waves in April and May led to a delayed summer beach width recovery. This delayed recovery resulted in June beachgoers having to deal with unseasonably narrow, dry beaches with the high tides in the late afternoons through the first half of June. We have only seen a similar large spring wave anomaly one other time in our 23-year hindcast record, and that was in 2017, which we will talk some more about soon. So this is where we are now in time, at the far right-hand side of these plots. So let's look ahead to see what we might expect to see this winter. Our Waves and Beach outlook is based on the historical relationship between the Oceanic Niño Index, or ONI, and our wave and beach width data sets. Everyone has likely seen this historical La Nina, El Nino index time series in some form before, demonstrating how the strong El Niños since the mid-1960s have been getting progressively stronger, but also farther apart. On the right-hand side, you can see we are currently about 7 years out from the last El Nino in 2016 and are officially in a La Nina. This is the third La Nina winter in a row, a triple dip, which is uncommon. Our probabilistic outlook uses an ensemble of ONI forecasts for the coming months, made by different climate centers around the world, which are shown in the spaghetti plot on the right panel. An interesting thing to note is that the majority of the ONI forecasts have the ONI going from its current -1 La Nina state to the 0 neutral state sometime between February and May. A recent article in the San Francisco Chronicle noted that a similar transition occurred in the 2016-17 winter, the year after the 2016 El Nino, and that resulted in late winter storm activity and precipitation. In our 2017 wave record, there were above average waves in the months of November and February, and then higher than normal spring waves as well, and a delayed beach recovery, just like we saw in 2022. So this is something to look out for. This is how we are going to look out for it, by updating our MOP seasonal average curves in real time for 2023, which are the solid red lines on the left, and we are going to compare what happens to the averages from 2017, the red dotted lines. Because the running averages use a 45-day or plus-minus 22-day filter window, our real-time beach widths estimates lag real-time by about 22 days. We can look a little farther down the road with waves by including a 7-day wave forecast in green in the lower panel, so the average wave line is only 15 days behind real-time. In the upper panel, you can see we are starting out the year wider than 2017, so we have that going for us. And as far as the waves go in the lower panel, we are running below 2017 and don't seem to be on track for an early winter above average waves like 2017, even including the storm we had last week and the forecasted event for this week that is shown. But the North Pacific is awake now, so we'll see how this all plays out in the coming weeks. So, in summary, the San Diego County beaches are currently in a post-El Nino-like state after the January 2021 extreme event, but we're hoping that they will recover more quickly in the coming years compared to 2016. We are monitoring whether the 2022-23 winter season wave and beach width behavior mirrors the 2016-17 winter, and we are developing ways to extend the MOP wave and beach predictions to all California state beaches using our San Diego County data for validation. Thank you very much, and I will now take questions.